So in this lesson, I'm going to tell you about big O notation. You've probably seen big O notation if you have taken some algorithm courses. You can see the Wikipedia's definition on my slides, but in simple words, it describes your code's time and space complexity. You need to understand this concept to judge how slow or fast your solution is. In this section, we will review the basics of big O notation. If you are discovering it now, you may find the concept complex at first, but as you progress in your preparation, it will become easier. So let's start with the time complexity. The time complexity is the amount of time necessary to execute an algorithm. It does not measure the actual time taken to run your algorithm. Instead, it measures how the time taken scales with a change in the input length. So let's take this example. Here you can see that the function has one instruction, and whatever values A and B have, the runtime will always be approximately the same. In this case, we say that the time complexity is constant, or O of 1. And now in this example, we just added a new instruction. Same than before. Even though we have two instructions, the runtime will not change depending on A and B inputs. So this function is still constant in time. Now, in this example, you can see that we have an array. We can say that the size of the array is n. The runtime in this case will depend on n. If n is equal to 1, it's not going to take the same amount of time than if n was equal to 1 million. So in this case, we will measure the time complexity by looking at n. Here we have a for loop, and we are looking at all the elements in the array. So we can say that the runtime is linear, or it's O of n. In this third example, you can see that we have two imbricated for loops. The two loops are going to run n times each one. So the complexity will be n times n. Therefore, we can say that the runtime is quadratic, or we have O of n squared. Okay, now let's look at the logarithm. What you have here is the code of a binary search. Okay, now let's take an example. Here we have an array, and this array has 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. What we're looking for is 12 inside of this array. So if we are using a binary search, what we are doing is that we're going to look between the first element till the end of the array. And we are going to search for the middle of this array. Since this array has 9 elements, we are going to look for the 4s. So 0, 1, 2, 3, and 4. The index 4 has the number 40. 12 is inferior to 40. So what we are doing is that we are going to look at this new range between 0 and 3. We're eliminating the 40. We know that the element that we're searching for is not here. So we are looking at the index that is below 4, so which is 3. Now we are still looking for the middle element, which is going to be 6. 12 is superior to 6. So now we are going to look at those two elements, because we know that 12 is under 40, but above 6. Again, we are looking at the middle element, which is going to be 12. And here we are, we have our target. With every iteration, the size of our search list shrinks by half. Therefore, traversing and finding an entry in the list takes logarithmic time, or O of log of n. Okay, now let's see the exponential time. 2 exponent n specifies a growth rate that doubles every time the input dataset is added. So to understand what is happening here, we are looking at this example. If n here is equal to 4, what we are going to do is that we are going to have 2 branches. Then when we are f of 3, we are going to still have 2 branches, and so on. Because the growth rate is going to double every time that we have the input, we can say that we will have an exponential time, or O of 2 exponential n. Something important with big O notation is that it only describes the growth rate of algorithm in terms of mathematical function, rather than the actual running time of the algorithm on some machines. So if we look at this example, what we see is that we have O of n and another O of n, which is O of 2n. But it doesn't really matter that we have twice this function. We can directly simplify by saying that this is O of n. The same principle goes for non-dominant terms. When we have n squared plus n, all we care about is the growth rate. So we can drop the n, which is the non-dominant. This way we can simplify and say that we have O of n squared. It goes the same for the next example. O of n plus log of n can be just O of n, which is superior of log n. Same again for the next example. We only need to keep the dominant. Now let's look at the space complexity, which is the amount of memory or space used by an algorithm. During the interview, we do not include the space of the input values. We only look at the additional space that we will need to resolve a problem. So now when we look at this example, we are not actually adding any values besides the input. So the input is in an array, and we don't need to count it. So the space complexity is constant, which is O of 1. Now, in this case, we are actually adding some space as we are creating an array inside of the function. So we know that the second array is equal to the array. So we can assume that it's the same size. And in this example, the space that we have will be linear, O of n. So now in terms of recursion, we also use space. So if we look at this example, we have our function sum, and we are using some recursion. And if we look at the stack, if we start with n equal to 4, then the next recursion would have 3, 2, 1, 0. Everything that we have is in the stack, and it counts. So we will also have O of n. So let's take some examples. What do you think this is? Well, the time complexity will be A times B. The reason is that we have 2 different arrays here. We have array of A, array A, and array B. And we don't know their sizes. So we can suppose that array A has the size A and array B has the size B. And because we don't know which one is bigger, we cannot even just keep the dominant. So both matters in this case. That's why we say that in time and in terms of time complexity, we have A times B. In terms of space, it's constant. We're not using anything besides the input. Okay, how about this one? Well, this one, it's a binary tree. And in terms of time complexity, we say that it's O of n because we are looking at all the nodes of our binary tree. We are looking at them only once. We start with the root, usually, and we're looking at the left node and the right node until we've looked at all the nodes of our tree. In terms of space, because we're using some recursion, we are going the deepest in our tree. The space that we are going to use is the tree's depth. How about this one? Well, this one is A divided by B. And the reason is that the while loop counts the number of iterations and has the variable result will become equal to A divided by B. Then we will have the root of A divided by B. In terms of space, once again, we're not using any space besides the inputs, so the space-time is constant. You can find the cheat sheet of Big O notation on bigocheatscheat.com. And that's it. Let's keep going.